Hi, this is Jeff Heaton. Welcome to Applications of Deep Neural Networks with Washington University. This is Module 13, Other Neural Network Topics. Part 2, Neural Network Ensembles. We'll go ahead and run the helpful functions that are at the top of every module. We'll start by looking at log loss because we're going to evaluate an ensemble for a Kaggle data set that is used with log loss evaluation. If I show you this, the output from this, you'll see basically a prediction accuracy and now it's in scientific notation, so that's a little bit inconvenient. But here you can see this tells you if you predicted 1.0 and it was in fact 1.0, for all of these, 1.0 was the right answer. So you predicted 1.0, and it was in fact 1.0, your log loss contribution on that would be 0. However, if the output should have been 1, but you only had a probability of 0.9, so your neural network wasn't quite as sure about the right answer. It got the right answer, just wasn't as sure about it. In that case, you would have a log loss of 0.1. Similarly, if you only gave it a 0.8, you would have a log loss of 0.22, and so on and so forth. You can see your log loss in Kaggle competitions, a good log loss is right around 0.35 to 0.22 or so. Often you won't see lower ones. It depends on the competition. So here, and then any log loss that's up around above 0.5, especially above 0.1, is horrible. So you want to avoid those sorts of log losses at all, if at all possible. Here we look at somewhat the opposite of that. If your log loss was 0.1, which is a pretty good one, your prediction accuracy was about 0.9. If your log loss was around 0.2 log loss, you were getting around 0.8. Now, log losses are good because they're a very good measure to fit your neural network against, but they're a very bad measure for explaining to non-data scientists, non-machine learning people. You don't want to go to an executive and say, okay, we've got a 0.01 log loss. I'm pretty happy. They're going to say, what are you talking about? Prediction accuracy is a better measure when talking to other people who are not data scientists, the muggles of the world, so to speak. Here we are dealing, the next thing we want to deal with for this is looking at feature importance. So now that we've got the log loss out of the way, let's look at how we can determine which features are actually important. This is a pretty good paper for feature importance because it evaluates quite a few different ways of evaluating feature importance with it. It's a 2004 paper, but a lot of these are still used. One of my favorite feature ranking methods is input for perturbation, and it is covered in this paper. This is also a unique paper because I like the last names of two of these researchers. You have literally Dr. Joy and Dr. Death on the same paper. I'm not kidding. You can't make this up. But it's those are two of the researchers, very good researchers in their respective field. But that is their paper. Input perturbation, which is what we're going to see, is actually something invented by Bremen originally for random forests. And the implementation of this is actually in a paper that I co-authored. I did a couple of things in this paper, but one thing that I did introduce was to create a TensorFlow compatible perturbation ranking algorithm, among others, and sort of a hybrid algorithm that I was introducing with this paper. Perturbation ranking is really pretty cool. It is a way of evaluating any type of machine learning model that you might have, neural network included. It doesn't analyze the weights of the neural network. It doesn't do anything that would tie it to that particular ranking or to that particular model type. What it is going to do is evaluate a trained neural network on any data set that you want. And that part is great too. It's not looking at the weights. You could take data that you got maybe a year after you fit the neural network, and you can see which features are still the most important with new data. Now the data has to be supervised. You have to have the correct labels for it. So this is how perturbation works. It is going to, say it's a simple data set like your iris data set. It is going to loop over all 4 of those input columns, so your measurements, your 4 inputs for the iris, or if you're dealing with the miles per gallon data set, it would go across your input predictors where you have the acceleration, all those different fields. And one by one, it is going to take each of those inputs and shuffle them. Now, if you take a column to data and you shuffle just that column, all the other columns stay fixed, you've effectively destroyed that column because you've almost randomized it. But this is better than, say, there's other ways you could destroy a column. You could set it all to 0. You could put in random number values. The problem is you don't know, I mean, say you set it to 0. What if that column was pretty close to 0 anyway? Or setting it to random numbers. What range? You'd probably want to sample that column and figure out the range. But the neat thing about just shuffling that column is that that column now, it has exactly the same min and max. It has exactly the same standard deviation. It has exactly the same mean. All these statistics are the same, but it's useless because you flipped it all around. Then you evaluate that neural network with that column damage, and you see what the error is. So you've damaged one of the columns, your error should go up. And the more your error goes up, the more important that column was. If you destroy a column and the error stays about the same, the neural network is really saying, you know, that column was not that important. You destroyed it, had me evaluate it, and it's still there. The column's not still there, but my prediction accuracy is still there. Then you restore that column, move to the next one, and you repeat it. You do this process for every single column in the data, and you look at all those errors, and whichever column resulted in the biggest error increase from you damaging that column, that is the most important column. And that's what this code does. We loop across all of the columns, we randomly shuffle that column, and then we evaluate the error. We have to know if it's regression or classification at that point. If it's regression, we evaluate the error based on mean squared error. If it's classification, then we evaluate the error in log loss. And we keep track of all these errors as we go through. And we kept the original values so that the destruction was not temporary. You don't want to leave a path of destruction in your wake. You don't want to destroy the first column, then destroy the second. You need to restore it. You need to evaluate each column destroyed independently. And then we report the error. And the error, whatever column had the maximum error, we divide it by. So whatever column had the maximum error, that's going to be 1.0. Always the most important column will be reported as 1.0. And then some decreasing value that's proportional to that maximum error going on downward as we predict, as we evaluate the importance of the other columns. Let's go ahead and run this. This doesn't do anything. This just gets our function into there. So we've got the perturbation rank. This is the same function that I published, mostly the same function that I published with the paper that I cited above in 2017 that I did with McElwee and Kennedy, my co-authors on that particular paper. We presented it at the IJCNN conference in Alaska. Okay, so this is... Now we'll see how we can do this on classification. So we'll run that perturbation rank function that we just created for the iris data set. This is training the iris data set, so this runs for a little bit, and then it completes. And now we will rank the results. You can see that the petal width is the most important. Petal length is also important. The sepal is just less important. You could probably get decent accuracy not even using the sepal, but it is still definitely important. We will do now regression perturbation ranking. That'll be the miles per gallon data set. We run it, and it hits early stopping, and we'll evaluate it. Now notice one thing too, we're passing in the names of these columns. We remove the miles per gallon. You always remove the target. I also remove the species here. You're not evaluating the importance of the target. The target would be very important in predicting itself. You're not training on the target, so don't evaluate its importance. You'd get an array error here because you would have one too many columns in there if you were trying to pass that in. So now we go ahead and run the feature importance. We can see that weight is the most important. That makes sense. The year produced for the car. Year produced is not quite as important. And we continue. Now, I sometimes get questions about error versus importance. Error is simply the root mean square or log loss, depending on if you're classification or regression, that resulted. So as you can see, cylinders is not that important. The error was only about 9.9. Not too bad of an error. That's why the importance was smaller. The error really shot up when you destroyed the weight column. So the max is always taken as your baseline, and then the importance is simply this value divided by the max. Well, 23.429 divided by itself is going to be 1. X over x is 1. But here, this would be 17 divided by 23. So that's going to be the 0.74. So these don't sum to 1, as you can clearly tell. All this is the proportion of this particular column to the error to the largest error, to the most important column. So that lets us evaluate the feature importance. Next, we're going to look at a Kaggle competition. The biological response data set. This is an older data set, but it is essentially what you are doing is you are looking at data that have a large number of columns but not too many rows. You're trying to predict if an organism will elicit a biological response. It'll respond to something under a variety of conditions. So this is this competition. This was 5 years ago, and the leaderboard, you can see the individuals who competed in this. This is a competition that actually have met the individual who Jeremy Aiken, anyway, one of the individuals on the winning team. He went on to create a company called Data Robot that I've worked with in a variety of situations. So this is the competition. The data they give you, there's really not much they can say about the data. The response is a 0 or a 1. The columns, there's a lot of columns. This is the challenge of this one. There's 17, almost 1,800 columns, and they're redacted. They don't tell you a whole lot. So what we can do is, I already have this downloaded. Oh, and by the way, there is also an interview with Jeremy and his teammates. That is fairly interesting to read through for that Kaggle competition. I'm going to go ahead and run this so that we load that data set in. and then we're going to print out the statistics, the shape of it really. There's only 3751 rows, but look at all those columns. That's crazy. But this is the data set, and the neural networks can in fact deal with it. So this data are already pretty numeric. I am going to fit it. I'm going to increase the capabilities of this neural network just a little bit there. We have the neural network, and we are going to go ahead and train it. So we've trained it, and it's getting an accuracy of 77 and a log loss of 61. Not the best log loss in the world, but it works out. We also generate a Kaggle submission file. We saw examples of doing this previously in the Kaggle class session. This might be a further example for you for the Kaggle competition that we did earlier, if you happen to be looking ahead at the class. But we could literally submit that to Kaggle and get probably pretty close to that of possibly that of a score. So let's use that trained neural network that we have to find out which features are important. So we're running it through the Perturbation Ranking. By the way, the Perturbation Ranking would be a great candidate for parallelization. You could run it on Spark or on multiple cores, because you're going through all those columns and randomizing. You could literally put a separate CPU thread or core on every single one of those columns and just run the whole thing in parallel. We'll let this go ahead and train, and then, or not train, but make it through the rest, and then we'll analyze it. Okay, now that it's completed, you can see all those columns. I would really like to be able to remove columns, but you can see they're all pretty darn important. 1.0, 0.96, 0.96. There's just not a lot we can do here. The least important column is 0.93. So removing these columns sort of one by one in a piecemeal manner is not really doing a lot for us. Now in Kaggle, where you can get really good rankings, and this ensemble that I show you here, you might have to run it a few times to tweak it and get different results, but it'll place you usually in the top 10 of this Kaggle competition. Now this is because we're using newer technology than was available six years ago when this Kaggle ran. But this shows you that you can get some pretty good results from an ensemble. Now, what an ensemble is you're taking multiple model types. Like a random forest, that's an ensemble, but it's a whole bunch of trees all ensembled together by the random forest. We're ensembling at a much higher level. This is a heterogeneous ensemble. So you're taking random forests with neural networks and all these types together, scikit-learn model types, and we're going to ensemble them. So this is the code that I'm giving you, and this is very useful code. This is the same exact code, or very similar to my code, that I use when I enter Kaggle competitions to do my own ensembling. But notice the highlighted area. These are the scikit-learn model types that we're going to ensemble on. We're going to literally train this to all these model types, and we're going to create a resulting model that makes use of all of these, and it brings them all together. Usually, if you take two fairly good models and you generate their predictions, if you just average those two predictions together, very, very often you will get a better result than either of those two. If one of those neural networks or one of those models is better than it, it's better to do a weighted average so that the better one has a better weighting. This is what this process does. It basically uses a linear regression to figure out the weighting of all of these models. So some of these models are going to be better inherently than others. And what we do is we build that ensemble, and we do that by basically, we train each of these individually. That's why I have the loop here, where we're just looping over them one by one by one. I'm going to go ahead and run this so that it's actually going in the background. So it takes a little while to run. So what we do is we loop over these, we create all of the models, and we essentially just create out-of-sample predictions. So we run a 5-fold cross-validation, and that gives us an out-of-sample prediction for every single one of these models. We're not doing anything special at that point. We're looping over every single model. We're going to train in the 5-fold cross-validation, and we generate our out-of-sample predictions. Once we have those out-of-sample predictions, we can now blend the models. We're going to take a logistic regression, and we're going to build this data set that basically will have, we're not going to train on the original data anymore with the regression. We're going to train on these models. So we created basically 1, 2, 3, 4, 5, 6, 7. Yeah, 3 and 3, 7. So we're going to create a data set where basically it has 7 predictors. And those 7 predictors are going to predict one output. The predictors are going to be the out-of-sample predictions for all of these models. We're learning to use the predictions of these individual models as we're learning to create a final prediction based on the predictions of the other models. That's how it ensembles them together. That linear regression learns how to create that sort of, using the models, the 7 models that we created, those outputs become the input. It learns how to combine those all together and produce the best sort of output to that. Now this runs for a little bit. I will let it go ahead and continue. It's just working on model 1 now. And then when we have that final model created, we have to create our Kaggle prediction. All we do is we run those same models on it again, on the submission data that we're going to send to Kaggle. We get those 7 prediction numbers, we feed that into our linear regression, and it gives us a prediction for each of those. So these are computationally expensive because we're going to have to fit 7 models now where we just had to fit one before. This is the Keras neural network that we had before, and it basically just fits all of those. Now it's working on model 0, and it has to go through 5-fold cross-validation on every single one of these. So this goes for a little while. It's done with the Keras classifier. Now it's on the k-nearest neighbors. And by the way, k-nearest neighbors is normally really a pretty primitive model. It just finds maybe the 3, number of neighbors 3. It finds the 3 nearest rows to what you trained it on, and it just does a voting between those 3. For regression, it would simply sum them together and average them. But k-nearest neighbors is very different than a lot of the other models, deep learning included, so it often becomes a very good ensemble member to work with those other ones. So I'll time lapse this, and we'll go ahead and let it train completely through. Okay, once that completes, it's gone through all 10 of the models, and it generates the Kaggle submission file that you would actually upload. And that will get a much, you can try it yourself, it will get a much better result than any of the individual ones, and it will be near the top 10 of the actual Kaggle from that competition. That is the end of this part. We will continue with... That is the end of this part. Thank you.